final year exam. So now we will see the derivation part here. Demagnetizing and cross magnetizing conductors. So now, as I told you, armature reaction, it will take place because of the condition when we connect some load, then armature conductors will carry the current which will produce its flux, and that flux will interact with the field flux. Because of that, main flux gets distorted. So now this armature conductor or the armature current which is going to give rise to the armature reaction, it will be having two components, that is demagnetizing and cross magnetizing components. So how many amount of armature conductors are responsible for demagnetizing effect, and how many amount of conductors of armature are responsible for cross magnetizing effect, that derivation part we'll discuss here. Okay, so now here we are given with a DC generator. These are the poles which are going to carry the field winding, and this is the armature core which is going to carry the armature conductor. And now here see that there is a presence of field flux as well as there is a presence of armature flux. Because of that interaction, you can see that brush position has been displaced by an angle of theta from GNA to MNA, from GNA to MNA. So now how many amount of this armature conductors are responsible for demagnetizing effect, and how many amount of armature conductors are responsible for cross magnetizing effect, that we will see the derivation part now. Okay, the conductors which are responsible for producing demagnetizing and distorting effects is as shown in figure 5.3.1. so this is this is the armature section, right? So how many conductors are responsible for, or what is that, demagnetizing, and how many conductors are responsible for cross magnetizing, that we will see here. Okay. So now here you can see calculation of demagnetizing and cross magnetizing ampere turns. Let us find the number of demagnetizing and cross magnetizing ampere turns. Derivation part, you can see, you can start the derivation part from here, but before to that you need to draw these diagrams. These two diagrams are important for us, because referring to these diagrams only we are going to write all the derivation notations here. So you need to draw all these diagrams. This is for figure 5.31, which is going to explain for demagnetizing and cross magnetizing ampere turns derivation part. So referring to this diagrams, we are going to derive the derivation here. Calculation of demagnetizing and cross magnetizing ampere turns. Let Z is equal to total number of armature conductors. Z means total number of armature conductors. So these are all nothing but armature conductors which are equal to Z here, which are equal to Z. And then P is equal to number of poles, I is equal to armature current in armature conductor current in ampere, and this current I is equal to IA by 2 for simplex wave winding. If the winding, armature winding, it is made up of wave winding, then armature current value is given by IA by 2, and if it is made up of simplex lap winding, then it is denoted as I is equal to IA by P. If it is lap, it is IA by P. If it is simplex wave, then it will be IA by 2. And theta m is what? Forward brush lead, forward lead of brush in mechanical degrees. So here you can see that because of the armature reaction, what is going to happen is that the brush which is earlier there at the GNA, now it has been shifted by some angle to MNA. So now this angle is theta here. Okay, now this angle is theta. So from AOC region, similarly, then BOD region, you can see here, AOC is equal to BOD, that is responsible for demagnetizing armature conductors. So the conductors of armature which are lying in the range of from AOC, similarly BOD, all this much amount of the armature conductors and this much amount of the armature conductors, they are responsible for demagnetizing armature component. Similarly, the remaining conductors, COB, similarly AOD, they are responsible for cross magnetizing armature reaction effect. Okay, and now this angle in between AOC, the angle here is theta plus theta, that is 2 times of theta. Similarly, the angle between BOD is, here also it is theta, means here also it will be theta. Altogether, the area covered by the armature conductors, the angle covered by the armature, what is the demagnetizing effect of armature conductor cell is 4 theta. Similarly, the another 4 theta is for cross magnetizing armature reaction effect. And now theta m is the forward lead of brush in mechanical degrees. So here you can see that brush has been shifted from GNA to MNA by an angle of theta m. Theta m means mechanical degree. Brush shift in mechanical degrees. Okay. And now the conductors which are responsible for demagnetizing ampere turns are lying in the region spanning 4 theta m degrees. The region is between angle AOC and BOD as shown in figure 5.3.2. So this is our figure 5.3.2, figure 5.3.2, where the region AOC and similarly BOD, this is the total number of armature conductors which are responsible for demagnetizing effect. And now totally how much area they are going to cover. If this is theta, this is also theta, this is also theta m, this is also theta m. So altogether this area span covered by the demagnetizing armature conductors is 4 times of theta m, 4 times of theta m. So this is field flux winding and this is armature flux. So this is armature cross magnetizing flux component. Cross magnetizing, FC means cross magnetizing armature flux, and FF is main winding flux. Similarly, if you take this above diagram, this is for demagnetizing effect. For demagnetizing effect, this will be completely in opposition of FF. FF is moving from left to right, whereas FD is moving from right to left. So this is armature reaction demagnetizing component, whereas this is armature reaction cross magnetizing component. It will be trying to distort main flux, whereas this FD will be completely trying to counterbalance. It will be completely trying to cancel FF value. Okay.
Sir,
Yes.
sir, both the demagnetizing and cross magnetizing conductors will affect same cause, no, sir? Like it affects the main field flux.
Remember, this demagnetizing flux as well as cross magnetizing flux, they are the components of armature flux. Yes, soon after
Yes, sir.
connecting the load, you will observe that current will flow through the armature conductor, and that armature conductor will give rise to armature flux. And now this armature flux will be having two components, that is demagnetizing component, which will be completely opposite to the main flux. If main flux is moving in this direction, means and demagnetizing will be moving in the opposite direction. It will completely trying to cancel FF value. And the other component of the armature flux is cross magnetizing, which will be moving in the downward direction, right? And remember, this both FC cross magnetizing and FD demagnetizing, both are the components of armature flux. And these two components, which are the components of the armature flux, they will try to cancel, they will try to distort the main fielding wind flux, which is nothing but FF value. Are you getting? So now
Yes, sir.
if this is my armature core, then how much amount of the conductors of the armature are responsible for demagnetizing, and how much portion of the armature conductors are responsible for cross magnetizing, that we are going to calculate here. So if this is 360 degree, out of this 360 degree armature core area, we are saying that AOC and area, BOD area armature conductors are responsible for demagnetizing, and rest of the area, that is AOD and COB, it is responsible for cross magnetizing, right? And what is the area span? How much angle they are covering? Theta plus theta m plus theta m plus theta m. So altogether it is 4 times of theta m. This is the theta m, that is the area covered by, what is that? Conductors responsible for demagnetizing ampere turns. Okay, that is what we are seeing here. The conductors which are responsible for demagnetizing ampere turns are lying in the region spanning 4 theta m plus theta m plus theta m plus theta m, altogether 4 times of theta m degrees. The region is between angles AOC and BOD. AOC means this AOC BOD. Better you can consider 5.3.1 because this 5.3.1 indicates demagnetizing effect conductors, whereas this 5.3.2 indicates cross magnetizing effect conductors. But you remember one thing, this top region AOC and this bottom region BOD, these are the conductors responsible for demagnetizing. The rest of this left and right conductors, that is COB and AOD, they are responsible for demagnetizing, sorry, cross magnetizing conductors. Okay, armature conductors. The region is between angle COC and BOD is as shown in figure 5.3.2. Okay, total number of armature conductors lying in the region of EOC and BOD. So now in the region of wait a minute. Yes, sorry for the interruption. So where I was explaining for how many amount of conductors are responsible for armature reaction conductors. So total number of armature conductors lying in the region of AOC and BOD. So how many conductors are lying here? AOC and BOD. What is the area they are going to cover? Theta m, theta m, theta m, theta m. How many? What is the displacement angle here? Altogether 4 theta m. What is the complete degree here?
360 degrees.
360. Okay, so it will be 4 theta m by 360. And how many conductors are there? Conductors are nothing but Z. So total number of armature conductors lying in the region of AOC and BOD is equal to 4 theta m by 360 into Z. Okay, now since two conductors form one turn, so remember conductors means this is conductor 1 and this is conductor 2. So if I want to form one turn means I should connect conductor 1 to conductor 2. So this is conductor 1, this is conductor 2. So if I connect conductor 1 with conductor 2, then this is one complete turn. So to get one turn, how many conductors I should have? So now this is my one turn. How many conductors I should have? Two conductors, right?
Two, sir.
So to get one turn, I should have two conductors, right? So since two conductors form one turn, total number of turns in these angles is equal to, because these are nothing but what? Total number of conductors. But I want the information in terms of turns, means since it is in conductors, so if you convert that conductors information into turns now. So for that sake, total number of turns in these angles is, make it half, because half of the turn is nothing but one conductor. Yes or no? Half of the conductor is nothing but, sorry, one conductor is equal to half turn here. If I consider only one conductor, this is equal to half turn. For that sake, we are going to convert now this conductor information into turns, means so multiply the same expression 4 theta times Z by 360 by half into 4 theta m Z divided by 360. So after simplification, this 2 ones are, this will be 2 2s are, so this will be 2 theta m by 360 into z. So this is nothing but total number of turns in these angles. Okay, so these are nothing but total number of turns, but we are interested in what? We are interested in ampere turns. So these are turns. Z means conductors, that too in the turns information, but we are interested in ampere turns. So now if I want, already I got the information in terms of turns here. Now what is the thing? You multiply this thing with the current value. So demagnetizing ampere turns means just you multiply it with I now. So in that case, 2 theta m by 360 into Iz. So this is demagnetizing ampere turns for all the poles. But now if I want for per pole information, demagnetizing ampere turns per pole, then in that case for the same expression you multiply it with half. You multiply it with half means 1 by 2 into 2 theta m by 360 into Iz. So if I do that, this numerator 2 and denominator 2 both will cancel with each other, then you are left out with what? Theta m 360 by Iz. So ETD per pole is equal to Zi, that is Zi into theta m by 360. So this is nothing but demagnetizing ampere turns per pole, that is equal to Zi theta m by 360. Is it clear? So this is the derivation for ETD per pole. Is it clear, all of you?
Yes, sir.
First we should consider total area for what is that? Demagnetizing ampere turns, that is 4 theta m by 360 into Z. Convert this conductor's information into turns because we are calculating derivation for the formula ATD. A means ampere, T means turns. So convert this conductor's information to turns. So for that sake, what we are doing? Multiplying this information with half, because 2 conductors is nothing but 1 turn. Since it is in conductor information, if I want to convert in turns, then multiply it with half into 4 theta m by 360 into Z. So then you will be getting this formula. Now this is in terms of turns information. Convert this turns information in terms of ampere. So for that sake, for the same expression, just multiply it with current I here. Then altogether this will be demagnetizing ampere turns. But if I want in per pole information, is just you once again multiply it with half into 2 times of theta m by 360 into Iz. Then in that case, numerator 2 and denominator 2 will cancel. Then you will be left out with theta m by 360 into Iz. So this is nothing but ETD per pole, that is equal to Zi into theta m by 360. So this is the derivation for demagnetizing ampere turns per pole. Now let us calculate what is the formula for ATC per pole. ATC per pole means cross magnetizing ampere turns per pole. Now, the conductors which are responsible for cross magnetizing ampere turns are lying between the angles AOD and BOC as shown in figure 5.3.2. So angle between AOD and BOC means left and right area, that is AOD and COB, that is what is that? Left and right area. And what is the area now they are going to cover? Once again, theta m, theta m, theta m, theta m. Altogether here also it is 4 theta m only. So this much amount of the area. So this much amount of the area, now they are responsible for which effect? This much amount of the area of the armature conductors, they are responsible for
Cross magnetizing.
Cross magnetizing. Whereas this much amount of the area of the armature conductors, they are responsible for demagnetizing effect. Okay, altogether this will be giving us armature reaction effect. Now let us calculate ATC per pole. The conductors which are responsible for cross magnetizing ampere turns are lying in the region of AOD and BOC as shown in figure 5.3.2. Now total armature conductors per poles. So per pole armature conductors are how much? Total conductors are Z. Yes or no? In the beginning, we have assumed that total armature conductors are Z, and conductors per pole means it will be Z by P. It will be Z by P. Okay. From above, we have found an expression for demagnetizing conductors per pole. So demagnetizing conductors per pole, which is nothing but Z 2 theta m by 360. See here, demagnetizing conductors per pole, that is, what is that? Per pole. Per pole means altogether it will be 4 theta m, but for one pole it will be 4 theta m. Per pole means divided by 2, that will be 2 theta m. conductors are Z, and altogether the area is 360. So demagnetizing conductors per pole is Z 2 theta m by 360. So this is the amount of conductors per pole. This is the amount of conductors per pole which are responsible for demagnetizing effect. And these are the total number of the conductors per pole. So now I know the total amount of conductors in the armature. I know the total amount of conductors per pole that are responsible for demagnetizing effect. Then let us calculate how many amount of the conductors are responsible for cross magnetizing effect, that is cross magnetizing conductors per pole. So in that case, what is the total amount of conductors here? That is Z by P. That is Z by P. This is my total conductors, and conductors which are responsible for demagnetizing effect is what? Z 2 theta m by 360. So from these two, now you take the difference. So from both of these expression, what is common here? Conductors Z is common. So Z into 1 upon 2p minus 2 theta m by 360. So this is what? Cross magnetizing conductors per pole. This is cross magnetizing conductors per pole. And that too, now you convert this cross magnetizing conductors per pole into ampere conductors per pole. So if I want to convert this into ampere conductors per pole, just you multiply this above expression by current I here. Zi into 1 upon P minus 2 theta m by 360. Right. So what is the information here? We want in terms of ampere turns. But what is the information here? Ampere. Yes. Now the information is in terms of ampere conductors. So now you convert this conductors information into turns information. So what I should do now? How to convert this conductors into turns? By what factor I should multiply?
By 1 by 2.
By 1 by 2. Very good. So you can see here, since two conductors form one turn, so convert this conductors information into turns. For that sake, cross magnetizing ampere turns per pole is equal to whatever this expression we have obtained here, that is for cross magnetizing ampere conductors per pole, that is Zi into 1 upon P minus 2 theta m by 360. Just you multiply it with half. By doing this, you are converting conductors into turns. So 1 by 2 into Zi into 1 upon P minus 2 theta m by 360. So if you simplify this, Zi will be same. Then this 2 will be taken inside this bracket. Then it will be 1 upon 2P minus of numerator to denominator will cancel. Then you will be left out with simply theta m by 360. So cross magnetizing ampere turns per pole is nothing but Zi into 1 upon 2P minus theta m by 360. So this is the derivation for what is that? Cross magnetizing ampere turns per pole. And now while solving the problems using this ATC per pole and ATD per pole, you should make use of this formula. So ATD per pole is given by Zi theta m by 360, and ATC per pole is given by, see here, ATD per pole, that is demagnetizing ampere turns per pole. It is given by the expression Zi into theta m by 360, whereas cross magnetizing ampere turns per pole, that is ATC per pole, is given by Zi into 1 upon 2P minus theta m by 360. So now in the problems, while you are solving the numerical problems based on ATC per pole and ATD per pole, and then they will be giving the mechanical degrees, by what angle the brush has been shifted. Sometimes it will be given in terms of mechanical degree, sometimes it will be given in terms of electrical degree. So how to convert that mechanical degree in terms of electrical or electrical back to mechanical? For that there is a formula, that is theta mechanical. This is nothing but brush shift angle in terms of mechanical. Okay, theta mechanical, theta refers to theta mechanical, that is given by theta electrical divided by pair of poles, where this numerator part is theta electrical divided by pair of poles, means that will be P by 2. So this 2 will appear in the numerator part. So altogether theta mechanical is equal to 2 times of theta electrical divided by number of poles P. So theta m is equal to 2 times of theta e divided by P. This is what you should remember while solving the problem. Whenever the angle is in terms of electrical, but we should consider this formula which is having mechanical brush shift. So if the value is given in terms of electrical, you should be careful that convert this electrical brush shift angle in terms of mechanical by making use of this formula. Only once you convert the formula, the value in terms of mechanical, then you can substitute this value here. Otherwise, if you directly substitute the theta E value, then your whole problem goes wrong. Is it clear how to convert this electrical angle into mechanical? The formula is very simple. Theta M is equal to 2 times of theta E divided by P, where P stands for number of poles. Now, since there is a armature reaction because of connecting the load, there will be some of the amount of the conductors responsible for demagnetizing effect and some amount of the conductors are responsible for cross magnetizing effect. So now, how to balance this armature reaction effect? How to balance this armature reaction effect? So what is the next procedure we should follow to avoid this reaction if armature reaction effect? So for that sake, we are going to connect some amount of extra winding, which can demagnetize, which can nullify the armature reaction effect. So how much amount of conductors they are responsible, how much amount of conductors we want to to avoid that armature reaction and all, we can see here. For neutralizing the demagnetizing effect of armature reaction, an extra number of windings are provided on each pole. Okay, so here already we know that armature reaction is going to take place in armature conductors. So now to avoid that armature reaction, we are going to connect some extra winding which are going to oppose to the armature reaction, and those amount of armature conductors or the turns, how they are going to be calculated, you can see here. To calculate its number of extra turns per pole. So these poles, they are these turns, they will be connected on the armature windings on each pole, and it is given by the formula ATD lambda divided by I, where lambda stands for leakage coefficient, I stands for current for shunt generator, and I is equal to ISH for shunt generator, and I is equal to IF for series generator. So this is the amount of current, this is the amount of the ampere turns that is supplied by the extra winding what we are going to connect on each pole of the armature winding, such that these windings it will take care of the armature reaction. If armature reaction is what is that 5 ampere turns, then this will induce armature reaction of minus 5 ampere turns. So altogether plus 5 minus 5, the effect might be 0. So this is how we are going to counterbalance the armature reaction by introducing some amount of number of turns on each pole of the armature winding. Is it clear? So till here you should write the derivation part if it is asked in the examination to derive the expression for armature reaction, that is ATC per pole and ATD per pole. So first you should draw the diagram. So this diagram is for demagnetizing effect and this diagram is for cross magnetizing effect. So show this vector diagram representation for both demagnetizing as well as cross magnetizing component, and directly you can explain for all this derivation part. You can explain for a whole this derivation part. You can write till here, till to this part you are supposed to write if they ask the derivation part for ATC per pole and ATD per pole. Is it clear, all of you? Yes?
Yes, sir.
Okay, so remember this formula because we are going to make use of this formula while solving the problems on ATD per pole and ATC per pole. ATD per pole means Z I theta M by 360, whereas ATC per pole means Z I into 1 upon 2 pi minus theta M by 360. This formula, remember, along with that theta M is equal to 2 times of theta E by P. Okay, so this is all about derivation part for ATC per pole and ATD per pole, and in the next class we'll discuss for commutation. Okay, so by this time now I'm going to wind up the class. Do you have any doubts?
Sir, problems on this.
So do you want to solve the problems now? Okay, you can discuss some problem here. You can see it now. Here, let us solve one problem based on ATC per pole and ATD per pole. All of you note down this problem statement. An 8-pole. All of you note down the problem.
We have DST class.
Sir, send the PDF of this problem, sir.
Okay, fine. So you will be solving this problem, right? Just you need to follow the formula ATD per pole Z I theta M by 360, then ATC per pole Z I into 1 upon 2 P minus theta M by 360. Just you be careful that what is the brush shift angle here. And the first case theta M is 0 means brush is lying on both what is that GNA. And in the second case, brush has been shifted from GNA. By what angle? By certain angle. But that angle is given here in terms of electrical. You need to convert this electrical angle into mechanical. So after converting, then you will be getting theta m as 1.5 degree. So that angle value you should substitute in ATC per pole and ATD per pole formula. And accordingly, you should get the value for ATC per pole and ATD per pole. Just I will solve for one problem. Don't just you can see here. I will just dictate the problem here. An 8-pole wave wound DC generator has 480 conductors, armature conductors. The armature current is 200 ampere. Find the armature reaction, demagnetizing and cross magnetizing ampere turns per pole if brushes are on GNA. First case is brush is on GNA, means what is the theta m value here? MNA and GNA are coinciding with each other. Then theta m will be what? See here.
0 degree.
If this is the brush, then this brush is coinciding. This brush which is on the MNA, it will be coinciding with GNA. Then theta m will be
0.
how much? 0.
0.
That is the first case. Just you can spend another 5 minutes. Okay. First case is brushes are on the GNA. Second case is what? Brushes are shifted 6 degree electrical from GNA. 6 degree electrical. So now they have given with theta E value here. Okay. For this, you should calculate ATC per pole and ATD per pole. Now, here you can see the what type of connection we are using here? Wave connection. So, wave connected. So, for wave connected, poles are given. P is equal to 8 and number of parallel paths for wave winding is A is equal to 2. Remember. Okay. Now, Z is equal to how many conductors are there here? 480 armature conductors. And now, here armature current IA is given as how much? 200 ampere. But now, IA is 200, but I want I value. I is nothing but IA by A for wave winding. So IA is 200, and what is A value for wave winding? It is 2. You have to be careful. You are doing them in the first step itself. Directly will be taking I value as 200. That is completely wrong. Your whole problem goes wrong here. First, you should need to check what is the type of connection. The type of connection here, it is given as wave winding. So you should take A value, number of parallel paths, A value as 2. Then you calculate the current value. I is equal to IA by A. IA is 200 and A is 2. So it will be, I value will be 100 ampere. And now first case, when the brushes are on GNA, GNA means theta m is 0 degree. So therefore, demagnetizing ampere turns are, that is ATD per pole. ATD per pole is given by Zi theta m by 360. Since we know that brushes are on GNA, GNA means what? Theta m is 0. If theta m is 0, then your ATD per pole is 0 value because theta m is 0. Then let us calculate cross magnetizing ampere turns per pole. That is ATC per pole is Zi into 1 upon 2p minus theta m by 360. Since theta m is 0, so once again this formula will be like Zi by 2p. Z is how much? 480. I is simply 100 and number of poles are 8. So substitute all that, then your ATC per pole will be how much? 3000, and it is unitless. Remember, it is not having any unit here. Okay, it is unitless, 3000. Similarly, go with the second case. Second case is what? Brushes are shifted by electrical angle 6 degree. So first you convert this electrical angle into mechanical angle. So what is the formula? We know that theta m is equal to theta E divided by P by 2. So theta E is, what is the value here? 6 degree. That is 6. Number of poles are 8 and this is 2. So theta m will be altogether 1.5 degree. Now once again you calculate ATD per pole. ATD per pole is Z di theta m by 360. Z is 480. I is 100 ampere. Theta m is 1.5 degree and this is 360. So after substituting and simplifying, you will be getting ATD per pole value will be 200. Okay, now similarly you calculate for ATC per pole. This is not ATD, this is ATC. Make this correction. Here there is some printing mistake. This is ATC per pole, which is nothing but Zi into 1 upon 2p minus theta m by 360. This is minus sign here. Okay, this is minus. So Z is 480. What is that? Z value is 480 and I is 100. That is altogether 48,000 into 1 upon 2p. Poles are 8. So 1 upon 16 minus theta m is 1.5. This is not 15. This is 1.5. This is 1.5 divided by 360. So after simplifying, ATC per pole with a brush shift of 6 degree electrical, the ATC per pole value will be 2800. Is it clear? In the same way, the rest of the problems will be there. Just you need to be careful that what is the type of winding and what is the type of brush angle they are giving, brush shift angle. If it is directly mechanical, take it directly. If it is electrical, convert that electrical angle into mechanical angle. This care you have to take, follow. Is it clear, all of you? If you do any
Yes,
mistake,
sir.
you are going to commit for 0 marks. What is that? You are going to get 0 marks if you do any mistakes. So on the precautionary step is you should check what is the type of connection, then what is the brush shift angle, whether it is in electrical or it is in mechanical, that you have to check. Okay, shall I wind up the class now? Do you have any doubts? Yes.
No, sir.
Okay, fine. Have a good day.
Okay, sir.